Hello there and welcome back to the Sleep Science Corner of the Internet, where big ideas move slowly and nothing demands too much of you. Right now, you're standing on the surface of a planet that feels solid and ordinary beneath your feet. Yet above and around you hums something invisible, something ancient, something quietly heroic. You don't see it when you look up at the night sky, but it's there, stretching far beyond the clouds, bending and bowing like a vast invisible shield. This is Earth's magnetic field, and whether you realize it or not, you are living inside it every moment of your life. You probably won't survive this video in the sense that you won't make it to the end fully awake. That's kind of the point, so before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're feeling chatty in that slow, end-of-day way, drop a comment with your location and local time. I love seeing how far these quiet conversations travel. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're imagining the magnetic field now as a gentle pressure, not pushing, not pulling, just holding. Scientists often describe it as a bubble, the magnetosphere, formed by Earth itself and shaped by the constant breath of charged particles blowing out from the sun. A mainstream historical fact worth letting settle in is this. Without this magnetic field, Earth's atmosphere would be far more vulnerable to being stripped away by solar wind. Much like what happened to Mars over billions of years. That's not science fiction. That's planetary history written across our solar system. As you breathe slowly, consider how strange it is that something so essential is so easy to forget. You don't wake up each morning thanking the geomagnetic field for deflecting cosmic radiation. You don't feel it doing its job while you sip coffee or scroll your phone. And yet, if it were to weaken or change dramatically, the effects would ripple quietly, then not so quietly, through nearly every system humans depend on. Historians still argue whether early navigators truly understood magnetism or simply trusted compasses as magical truth-tellers that pointed the way without explanation. The magnetic field is not a static thing. It is not bolted into place like a planetary accessory. It flows and shifts, generated deep within the Earth by the slow churn of molten iron in the outer core. That fact alone is enough to make you pause. Beneath oceans, beneath continents, beneath the place where you're listening right now, liquid metal moves in looping currents, and those currents give rise to the field wrapping around you. A quirky tidbit you can tuck away like a smooth stone in your pocket. The strength of Earth's magnetic field is not uniform. It's weaker over the South Atlantic, forming what scientists call the South Atlantic anomaly, a region where satellites are more likely to experience glitches. Even space hardware gets a little sleepy there. As you imagine this invisible shield, it helps to think of it not as armor, but as guidance. Charged particles from the sun are funneled toward the poles, painting the sky with auroras, curtains of green and purple light that dance silently above places like Alaska and Scandinavia. Ancient cultures noticed these lights long before they understood magnetism. Some thought they were spirits, others saw omens, and a few probably just stood there thinking, well, that's unsettling, before going back inside to stay warm. The idea that Earth's magnetic field could change sounds alarming at first, but change is actually its default state. Magnetic north wanders. It doesn't politely stay put for our maps. In fact, over the last century, magnetic north has been drifting faster than expected, prompting updates to navigation models. That's right, even GPS systems need occasional magnetic reality checks. A light joke for the road here. The magnetic field is basically that one coworker who keeps rearranging their desk, and everyone else has to adjust. You're easing into the realization that when scientists talk about changes in the magnetic field, they're usually talking about slow processes measured in decades, centuries, or millions of years. This isn't a switch that flips overnight. Historians still argue whether past mass extinctions had any meaningful connection to magnetic reversals, or whether those events were merely coincidental passengers on the same geological timeline. And yes, reversals have happened, many times. Earth's magnetic poles have flipped, north becoming south and south becoming north, with no evidence that life noticed in any dramatic way. However, that fact alone should soften some of the sharper fears that tend to circulate online at 3 in the morning. Early humans lived through these changes without compasses, without satellites, and without YouTube videos whispering about it into their ears. There's a tendency, especially in modern life, to assume that any planetary change must be catastrophic. But Earth has always been dynamic. Continents drift, climates shift, magnetic fields wander. The field weakening slightly over a few hundred years is not the same as the shield vanishing in a puff of cosmic smoke. A fringe but fascinating idea some researchers once entertained was that animals might sense not just the field itself, but its subtle fluctuations, almost like listening to planetary weather. While evidence is mixed, it's a comforting thought. Life tuned in to rhythms far older than us. As you settle deeper, let the magnetic field become a background presence in your mind, like the low hum of that fan beside you. You don't need to understand every equation or model to appreciate its role. It's enough to know that it's there, that it has changed before, and that it will change again, slowly, patiently, on a time scale that doesn't rush you. And maybe that's the quiet lesson tucked inside tonight's topic. Earth's magnetic field reminds you that some of the most important forces in your life are invisible, steady, and unconcerned with your schedule. They don't announce themselves. They just keep working, moment by moment, while you rest. You keep moving forward without really moving at all, drifting downward in your imagination, past soil and stone, past layers with names you once memorized in school and then promptly forgot. The crust slips by first, thin as an apple peel compared to what lies beneath. Then comes the mantle, hot, slow, patient. Nothing here is in a hurry. And finally, far below any place you could ever reach, you arrive at the source of that invisible shield humming around you. This is where Earth's magnetic field is born. You're hovering near the outer core now, a vast ocean of liquid iron and nickel swirling around a solid inner core like a heavy, glowing sea. A mainstream historical fact settles in here. Scientists figured out that Earth has a liquid outer core in the early 20th century by studying how seismic waves from earthquakes travel through the planet. Some waves slowed, some vanished, and the only explanation was a molten layer deep below. No one drilled there, no one peeked. Earth itself told the story through vibrations. As you watch this imagined ocean of metal move, you notice that it doesn't just sit there. Earth rotates, and that rotation twists the liquid iron into spiraling currents. Heat rises from the inner core, cooler material sinks, and the whole thing churns in slow, looping motions. This movement of electrically conductive liquid creates electric currents, and those currents generate magnetic fields. This self-sustaining process is called the geodynamo, a name that sounds like a superhero but behaves more like a very reliable appliance. Historians still argue whether the geodynamo has been operating continuously since Earth's earliest days, or if it flickered on and off in the planet's youth. What seems clear is that once it stabilized, it became one of the quiet prerequisites for complex life. Without it, the solar wind would have had a much easier time thinning the atmosphere, stealing away lighter molecules bit by bit. Again, Mars looms as a cautionary tale, like a sibling who skipped leg day and never quite recovered. There's something oddly soothing about knowing that the engine protecting you is powered by heat and motion, not intention. The Earth isn't trying to save you, it's just being itself. A quirky tidbit worth smiling at. The inner core, though solid, is not perfectly locked in place. Some studies suggest it may rotate at a slightly different speed than the rest of the planet. So while you're lying still, the very center of the Earth may be quietly doing its own thing, fashionably late to the rotation party. You imagine the magnetic field lines rising from this churning metal, threading upward through thousands of kilometers of rock and emerging near the poles. These lines loop out into space and back again, creating the familiar bar magnet shape scientists draw in diagrams. Of course, real life is messier. The field isn't perfectly symmetrical. It ripples and wobbles, shaped by turbulence in the core and by the sun's constant push from the outside. Think less polished sculpture, more lava lamp. For centuries, humans had no idea this was happening. Lodestones, naturally magnetized rocks, were known in ancient China and Greece, and compasses were in use by the 11th century, guiding ships across open water. But the idea that magnetism came from deep within the Earth took much longer to settle. Early theories involved giant magnets embedded in the crust or even celestial influences. Historians still argue whether some medieval scholars suspected an internal source but lacked the language to describe it. As you float here, you can almost hear the low, inaudible roar of convection currents, though in reality this motion is glacially slow. The liquid iron moves at speeds closer to a leisurely walk than a rushing river. And yet, over years and centuries, that's enough to reshape the magnetic field above. It's a reminder that power doesn't always announce itself with noise. Sometimes it just persists. There's a fringe idea that occasionally surfaces in scientific discussions, usually late at conferences or early in speculative papers. Could changes in the core subtly influence surface processes like volcanism or climate? Most evidence says the connections are weak or indirect, but the debate hasn't fully cooled. Historians still argue whether correlations seen in ancient records are meaningful or just the human brain desperately pattern hunting across deep time. You let your attention rest on the sheer scale of it all. The outer core is about 2,200 kilometers thick. That's more than 6 times the depth of the deepest ocean trench. And yet, its behavior determines whether your phone's compass points roughly north or slightly wrong, whether satellites need extra shielding, whether auroras stay politely near the poles, or wander closer to the equator to show off. A light joke drifts through. The Earth's core is basically running the longest, slowest science experiment imaginable, and we're all living in the lab without lab coats. No safety briefing either. Kind of just vibes and molten iron. What's especially calming, if you let it be, is how stable this chaos is. Despite constant motion, despite turbulence and heat and pressure beyond comprehension, the geodynamo keeps going. It falters sometimes. It weakens, strengthens, shifts. But it doesn't simply stop on a whim. Total shutdown scenarios make for dramatic headlines, but the physics suggests they're unlikely without major planetary changes. Like cooling so extreme, the core solidifies entirely. And that, thankfully, is not on the schedule anytime soon. So as you slowly drift back upward in your mind, carrying this image of a restless, glowing heart at the center of the planet, you can feel a strange reassurance settle in. Earth is active. Earth is alive in its own geological way. And the magnetic field wrapping around you tonight is not fragile glass, but the natural outcome of a planet doing what planets do best: moving, turning, and quietly enduring. You don't need to remember every detail. Just remember this feeling, that beneath your stillness, something vast and ancient is flowing, and it has been flowing for longer than any human worry ever has. You drift back up toward the surface, carrying that image of slow-moving molten iron like a half-remembered dream. And as you rise, you start to notice something very human creeping into the story. Curiosity, the urge to measure, to point at something invisible and say, yes, but how strong is it? And is it moving? And can we trust it not to wander off while we're not looking? This is where humans enter the magnetic field story not as passengers, but as quiet observers with tools. Long before satellites and sensors, people noticed that certain rocks behave strangely. Lodestones would tug at iron filings, nudging them into delicate little lines as if sketching the field itself. A mainstream historical fact settles in here. By the 11th century, Chinese navigators were using magnetized needles to find direction, and by the 12th century, compasses had spread to Europe, transforming navigation. For the first time, direction didn't depend on stars, coastlines, or luck. It depended on an invisible planetary force that didn't care if it was cloudy. Imagine how uncanny that must have felt. You're on a wooden ship, miles from land, surrounded by fog, and a small needle calmly insists that north is that way. No explanation, just trust. Historians still argue whether early sailors truly understood that compasses pointed to a magnetic pole rather than true geographic north, or whether that subtle discrepancy was noticed only after maps started looking a little off. As centuries passed, the tools became more refined. Scientists began to notice that the magnetic field wasn't constant. Measurements taken in the same place years apart didn't quite match. The needle drifted. This was unsettling. After all, people like their invisible forces to be dependable. By the 19th century, global efforts were underway to map Earth's magnetic field, with ships crisscrossing oceans, specifically to measure magnetic strength and direction. This wasn't glamorous work. It was slow, meticulous, and often seasick. You can picture it now. Sailors lowering instruments, scribbling numbers. I'm probably wondering why they didn't choose a nice desk job instead. A light joke floats by. The original magnetic field researchers were basically running a planetary Wi-Fi survey, except wetter and with worse snacks. One quirky tidbit to tuck in here. Some early magnetic observatories noticed daily fluctuations in the field, small wiggles that repeated every 24 hours. It took a while to realize these were linked to the sun, not the Earth, as solar radiation ionizes the upper atmosphere and subtly tweaks the field. Even before spaceflight, the sun was already photobombing Earth's magnetic measurements. As technology improved, so did our reach. In the mid-20th century, magnetometers became sensitive enough to be mounted on airplanes and ships, and eventually on satellites. This changed everything. Instead of inferring the field from scattered surface measurements, scientists could see it as a whole, a living shape surrounding the planet. Satellite missions like MagSat in the late 1970s and later missions such as ESA's Swarm constellation provided detailed global maps of the field and its changes over time. Historians still argue whether the biggest leap in understanding came from these satellites or from earlier theoretical breakthroughs that made sense of the data. It's the classic science tension: tools versus ideas. In reality, they quietly need each other. You let yourself imagine Earth wrapped in faint, glowing contour lines, like a topographic map turned inside out. Stronger here, weaker there. The South Atlantic anomaly shows up again, that magnetic dip where the field is unusually weak. Satellites passing through it sometimes experience glitches, flipped bits, or momentary confusion. Spacecraft engineers plan around it carefully, like drivers slowing down for a known pothole on the cosmic highway. What's soothing is how patient this monitoring is. Scientists don't panic at every fluctuation. They expect them. The field breathes. It pulses gently in response to solar storms, compressing on the day side of Earth and stretching into a long tail on the night side. When a strong burst of solar wind arrives, the magnetosphere shudders slightly, and instruments around the world register the disturbance like a distant thunderclap. There's a fringe but fascinating idea that ancient humans may have noticed magnetic changes indirectly, not through compasses, but through subtle shifts in auroral activity. Even if auroras appeared farther south during certain periods, they would have been impossible to ignore. Some rock art and old texts might hint at this, though evidence is thin and debated. Historians still argue whether such interpretations are inspired insight or enthusiastic overreach. You don't need to decide. You're just drifting, observing how measurement itself becomes a kind of dialogue between humans and planet. We ask questions by building instruments. Earth answers in numbers, and we spend decades translating. One particularly calming realization settles in. Measuring the magnetic field revealed not just change, but predictability within change. Scientists can model how the field evolves, how fast it drifts, how likely certain anomalies are to grow or fade. Navigation systems quietly update in the background, not compensating for magnetic wander without bothering you about it. Your phone doesn't gasp and say, "Oh no, north moved again." It just adjusts, and maybe that's the quiet miracle here. The more we measure, the less dramatic change feels. Knowledge turns cosmic uncertainty into manageable background noise. You imagine the magnetic field tonight not as a mystery, but as a monitored companion. Watched by satellites gliding overhead, logged by observatories humming away in remote corners of the world, and traced by invisible lines that scientists have learned to read, like a very slow, very large heartbeat. Another gentle joke drifts in. Earth's magnetic field has more tracking devices on it than a lost suitcase. And unlike the suitcase, it's exactly where it's supposed to be, just not always pointing where you expect. As your thoughts slow, you realize that measuring something doesn't make it less magical. If anything, it adds a new layer of wonder. The field is still invisible, still vast, still shaped by molten metal far below your reach. But now it's also something we can listen to, patiently, as it murmurs its long, unhurried story across centuries. And you're here, wrapped inside that story, comfortably unburdened by the need to check the instruments yourself. You don't stop drifting when time itself begins to stretch. Instead of moving through space now, you're gliding backward, sliding along a timeline so long it barely fits inside the word history. The continents blur, rearrange, collide, pull apart. Ice comes and goes. Forests rise, vanish, return. And all the while, the magnetic field above it all does something quietly radical. It flips. And this is where the idea of magnetic pole reversals enters. Not as a sudden disaster movie moment, but as a slow, almost absent-minded turn of the planet's internal compass. A mainstream historical fact to anchor you here: geologists discovered evidence of magnetic reversals in the mid-20th century by studying volcanic rocks on the ocean floor. As lava cools, iron-bearing minerals inside it lock in the direction of Earth's magnetic field at that moment, like tiny frozen compass needles. Layer by layer, the seafloor recorded a barcode of magnetic stripes: normal, reversed, normal again, stretching away from mid-ocean ridges. At first, this discovery was confusing. Then it became revolutionary. Those magnetic stripes helped confirm plate tectonics, one of the biggest unifying ideas in Earth science. So magnetic reversals weren't just curiosities. They were clues, quietly solving a planetary puzzle. Historians still argue whether the importance of magnetism in proving plate tectonics was fully appreciated right away, or only in hindsight, once the theory had already taken hold. You let that sink in. The planet has flipped its magnetic poles hundreds of times, and the rocks remember. A reversal doesn't happen overnight. It's not a dramatic snap where north suddenly points south while everyone's compasses spin like startled cats. Instead, the process unfolds over thousands of years. The magnetic field weakens, becomes tangled, sprouts multiple north and south poles in odd places, and then slowly reorganizes itself in the opposite orientation. For long stretches, there may be no clear north at all, just a messy, low-strength field doing its best. A light joke drifts by here. During a reversal, the magnetic field basically looks like it's had a bad haircut and is waiting patiently for it to grow back in properly. The last full reversal, known as the Brunus-Matayama reversal, happened about 780,000 years ago. Early humans were around. They hunted, gathered, made tools, and slept under the stars, entirely unaware that the planet's magnetic polarity had flipped. There's no evidence of mass extinctions or global catastrophes tied directly to that event. Life, it seems, barely noticed. That fact alone has a calming weight to it. Still, the idea of reversals has inspired plenty of fringe theories. Some have suggested links between reversals and climate shifts, volcanic outbursts, or even human evolution. Well, most of these connections fade under close scrutiny, but they keep resurfacing, especially when people learn that the field is weakening slightly today. Historians still argue whether these recurring fears say more about Earth's magnetism or about humanity's discomfort with slow, uncontrollable change. One quirky tidbit worth savoring: during some past reversals, the magnetic field may have dropped to as little as 10 to 20% of its usual strength. Even then, the atmosphere stayed put. The sky did not fall. Cosmic radiation levels likely rose somewhat, but not enough to sterilize the planet. Earth, it turns out, has backup systems: thick air, ozone layers, and sheer size, that all help share the load. You imagine the sky during one of these ancient transitions. Auroras might have appeared in places that never see them today, glowing faintly over regions closer to the equator. Nighttime skies could have shimmered more often, strange and beautiful, prompting wonder rather than panic. If you were there, you might have looked up and thought the gods were restless, then shrugged and gone back to your fire. What's especially gentle about this process is its irregularity. Reversals don't follow a schedule. Sometimes millions of years pass without one. Other times they cluster more closely together. The magnetic field seems to have moods, long stretches of stability punctuated by restless periods. Scientists can calculate average intervals, but averages don't make predictions. Historians still argue whether patterns seen in reversal timing are meaningful cycles or statistical coincidences that look more intentional than they really are. And then there are excursions. These are like half flips, moments when the magnetic field weakens and partially reverses, only to snap back to its original orientation. One well-known example, the La Champs excursion about 42,000 years ago, coincided with a significant drop in field strength. Some researchers have speculated about increased radiation exposure during this time, even possible impacts on Neanderthals or early Homo sapiens. The debate remains lively. Historians still argue whether the timing is suggestive or merely overlapping timelines doing what timelines often do. You don't need to solve that argument tonight. You're just floating, watching Earth rehearse change without drama. There's something oddly comforting in knowing that the magnetic field has never really broken. It bends. It fades, it reorganizes. But it doesn't shatter. The geodynamo keeps turning, even when its output looks messy from the surface. That messiness is not failure, it's process. Another small joke slips in. If Earth's magnetic field had a resume, successfully flipped poles without destroying biosphere would be listed under special skills. As you continue drifting through deep time, you realize that reversals challenge a very human instinct, the desire for permanence. We like our north to stay north. We like our maps to stay useful. But the planet doesn't share that preference. It operates on its own scale, where thousands of years are just a thoughtful pause. And here you are, listening, resting, wrapped in a magnetic field that has survived far more change than any single species, civilization, or worry ever could. Whether the next reversal happens in 1,000 years or 100,000, it will unfold slowly, politely, without asking for your attention. You can let that knowledge loosen something in you. Change doesn't always mean danger. Sometimes it just means the planet stretching, turning over in its sleep, and you, safe inside that turning, can keep resting too. You ease forward from deep time back towards something more familiar, something human-sized. The planet is still old and patient beneath you, but now there are hands holding tools again, eyes squinting at horizons, minds quietly depending on an assumption that feels solid until it isn't. North is north, or at least it usually is. This is the moment when compasses start to lose a little confidence. A compass seems so calm, so sure of itself. A small needle balanced just right, aligning obediently with Earth's magnetic field. For centuries, that tiny movement has meant safety, trade, exploration, and occasionally the difference between finding land and not. A mainstream historical fact to ground you here. By the age of exploration, European navigators relied heavily on magnetic compasses, especially when clouds hid the stars. Entire empires leaned on that quiet needle without ever fully controlling the force guiding it. But the compass has always been a translator, not a truth teller. It points to magnetic north, not geographic north, and the difference between the two, called magnetic declination, changes depending on where you are and when you are. Early mapmakers knew this, at least vaguely, and tried to account for it. Still, errors crept in. Ships ran aground. Routes wandered. Historians still argue how many famous navigational mysteries were really just magnetic misunderstandings, dressed up as bad weather or poor judgment. You imagine standing on the deck of an old ship, compass in hand, waves slapping wood in a steady rhythm. The needle trembles slightly, not because it's broken, but because the field it's listening to is never perfectly still. Even today, magnetic north drifts by tens of kilometers each year. In recent decades, that drift has sped up, sliding from Canada toward Siberia like it has somewhere better to be. A light joke floats through. Magnetic north didn't ghost us. It just moved without updating its address. This wandering isn't dangerous on its own, but it does create inconvenience. Modern navigation systems, including aviation and military maps, rely on precise magnetic models. When north moves faster than expected, those models need updating sooner. Runway numbers at airports, which are based on magnetic headings, sometimes have to be changed. Imagine repainting giant numbers on concrete because the planet quietly adjusted itself while no one was looking. One quirky tidbit worth keeping close. Some airports have already renumbered runways because of magnetic drift. The planes didn't change. The Earth did. As the magnetic field weakens during certain periods, like before a reversal or during an excursion, compasses become less decisive, the field lines flatten, the signal softens. In extreme cases, multiple weak poles can exist at once, confusing any device that expects a single, confident direction. It's not that compasses stop working entirely. They just start shrugging more often. Most historians still argue whether ancient travelers noticed periods when navigation felt subtly off, even without understanding why. Oral traditions from some seafaring cultures speak of times when the sea paths felt unreliable, when journeys required more stars, more landmarks, more intuition. Whether this reflects real magnetic variability or poetic metaphor is still debated and likely always will be. You can feel how this topic brushes up against a deeper discomfort. Humans like fixed points. We like knowing where we are in relation to something stable. When north itself becomes negotiable, it pokes at that preference. But it's worth remembering that compasses are just one layer of navigation. Long before them, humans navigated by stars, coastlines, winds, animal behavior, and memory. The compass didn't invent orientation. It just made it portable. There's a fringe idea that sometimes appears in speculative research. During periods of very weak magnetic field, humans might have relied more heavily on celestial navigation, perhaps even shaping mythologies around stars and skies. It's a lovely thought, though evidence is thin. Historians still argue whether cultural shifts attributed to the sky changing reflect astronomical events, magnetic ones, or simply the storytelling instinct doing its thing. As you let your thoughts slow, you realize that modern life has quietly insulated you from most of this uncertainty. GPS doesn't care much about magnetism. It listens to satellites and atomic clocks, not molten iron. Your phone can point you north even if the magnetic field throws a mild tantrum. But backup systems still matter. When GPS signals are lost or jammed, magnetic navigation steps back into the spotlight, and suddenly those slow changes feel a little more relevant. Military planners, pilots, and surveyors pay close attention to magnetic models for this reason. They don't panic when north drifts. They adapt. Updated charts are issued. Software is patched. Quiet adjustments ripple through systems you never see. The field changes. Humans respond. This dance has been going on for centuries, just with better instruments and fewer dramatic shipwrecks. Another gentle joke wanders by. Earth moves north. Humans update a spreadsheet. Everyone pretends that was the plan all along. What's calming, if you let it be, is how forgiving the process is. The magnetic field doesn't yank the rug out from under you. It nudges, it drifts. It gives decades of notice. Even during reversals, when compasses would have been largely useless, life carried on just fine without them. Navigation adapted, or rather remembered older ways. You imagine a future moment, far from now, when the field is weaker and messier, and compasses point in confusing directions. Someone shrugs, switches modes, and uses another reference. The world doesn't stop. It just reroutes. And maybe that's the soft lesson here. Orientation doesn't come from a single needle. It comes from layers of information, from flexibility, from not insisting that the universe stays still so you don't have to adjust. The magnetic field has always been a moving target. We just built tools that learn to move with it. As your breathing evens out, the idea of a wandering north feels less unsettling and more human. A reminder that even our most trusted guides are part of a living system, not a rigid rulebook. North drifts, maps update, journeys continue. You don't need to hold a compass tonight. You're not navigating oceans or skies. You're just resting, letting direction become optional for a while. The planet can keep shifting its invisible lines. You're allowed to stay exactly where you are. You let the idea of wandering north fade gently, and as it does, the sky begins to take over your imagination. Not the familiar sky you glance at between buildings or through a windshield, but a wider one, darker and deeper, stretching from horizon to horizon. This is the sky where the magnetic field makes itself visible, not as lines or numbers, but as light. Auroras. You've probably seen photos, green curtains, purple arcs, rippling like slow-motion flames. When they look unreal, like the sky briefly forgot its job description. A mainstream historical fact settles in here. Auroras occur when charged particles from the sun are guided by Earth's magnetic field toward the polar regions, where they collide with gases in the upper atmosphere, causing them to glow. Oxygen gives you greens and reds. Nitrogen adds blues and purples. It's physics doing art on the side. Under a stable magnetic field, auroras mostly keep to high latitudes, forming oval-shaped rings around the poles. People in places like northern Canada, Scandinavia, and Antarctica get front-row seats. Everyone else gets the occasional surprise during strong solar storms. But when the magnetic field weakens or shifts, those boundaries loosen. The auroral ovals expand. The lights wander. What you imagine standing somewhere far from the poles, maybe a quiet field, maybe a city that rarely looks up, and seeing the sky begin to shimmer. Not violently, just softly. A pale green glow where there shouldn't be one. During periods of magnetic disturbance, especially in the past, this likely happened more often. Historical records describe strange lights in the sky seen as far south as Rome or China during intense solar events. Historians still argue whether some ancient descriptions of burning skies or dancing spirits were auroras seen at unusually low latitudes, possibly during times when the magnetic field was weaker. The language of the past is poetic and imprecise, and that makes interpretation both irresistible and frustrating. There's a quirky tidbit that often surprises people. Auroras make sound, or at least, some people report hearing faint crackles or hisses during intense displays. The phenomenon is still debated. Some scientists suggest it's a psychological effect. Others propose electrical interactions near the ground. Historians still argue whether historical accounts of auroral whispers reflect a real physical process or the brain filling in sensory gaps during an emotionally charged experience. As you imagine the field changing, you picture auroras becoming more democratic, less exclusive, a cosmic light show touring new regions. During a magnetic reversal or excursion, with the field weakened and tangled, auroras could appear at much lower latitudes on a regular basis. The sky would be more active, more expressive, more distracting, especially if you're trying to sleep under it. When a gentle joke drifts by, if the magnetic field weakens enough, the auroras basically go on tour and forget to check the venue size. But there's a quieter side to this beauty. Auroras are a visible sign of energy entering Earth's atmosphere. When they move closer to the equator, it means more charged particles are interacting with the planet in places that don't usually see them. This doesn't automatically spell disaster, but it does hint at increased radiation at high altitudes and in space. For most people on the ground, the atmosphere remains a very good shield. Up high, things get more interesting. During strong geomagnetic storms, modern pilots sometimes reroute flights away from polar regions to reduce radiation exposure and avoid communication disruptions. This is already standard practice. Not a reaction to some hypothetical future. The magnetic field flexes, humans adjust quietly. Historians still argue whether similar disruptions might have affected early radio communication in the 20th century before the connection to solar activity was fully understood. You let your thoughts linger on how humans have always looked to the sky for meaning. When auroras appeared in unexpected places, they were often read as omens of war, of change, of divine displeasure. It makes sense. The sky is supposed to be predictable in its unpredictability. When it breaks pattern, attention follows. A fringe idea sometimes discussed is whether increased auroral activity during magnetic excursions influenced myth-making on a broad scale. Did more frequent skylights feed stories of gods, dragons, or spirits descending from above? It's a romantic hypothesis, and while evidence is thin, it highlights how environmental changes can shape imagination as much as survival. You breathe slowly and imagine auroras not as warnings, but as messages written in light. The magnetic field, normally silent, briefly becomes visible, like a mood ring for the planet. Stronger here, weaker there, restless tonight. What's calming, though, is the scale of protection still in place. Even during past periods of weakened magnetic field, Earth's thick atmosphere absorbed most harmful radiation. Life endured, adapted, continued. The sky may have been brighter, more dramatic, but it wasn't lethal to the world below. Another soft joke floats through. Earth basically said, I'm feeling a little exposed tonight, and responded by turning on the lights. As the imagined sky slowly dims, well, you realize that auroras are reminders, not threats. They show you that the magnetic field is dynamic, responsive, and alive. When it changes, it doesn't do so silently. It paints its movements across the heavens, inviting anyone paying attention to notice. And tonight, you don't need to decode the message. You can just enjoy the glow, real or imagined, as it fades into darkness. The sky returns to its usual quiet, the auroras retreating back toward the poles or into memory. The magnetic field settles into the background again, invisible but present, like a protective hush over the planet. And under that hush, you let your thoughts soften, the last traces of glowing light dissolving as sleep pulls a little closer. As the last imagined aurora fades from the sky, your attention drifts upward, higher than clouds, higher than weather, on into a realm where Earth feels less like a home and more like a piece of hardware moving through a very busy neighborhood. This is near-Earth space, where satellites glide in careful paths, and the magnetic field does some of its most underappreciated work. You don't usually think about satellites. That's part of their success. They're meant to be forgettable, quietly handling GPS signals, weather data, internet traffic, and television broadcasts without asking for applause. A mainstream historical fact to ground you here: the first artificial satellite, Sputnik 1, launched in 1957, and almost immediately scientists realized that space was not empty. It was filled with charged particles trapped by Earth's magnetic field, forming regions now known as the Van Allen radiation belts. These belts are like cosmic holding zones, where energetic particles spiral along magnetic field lines, bouncing back and forth between hemispheres. They're not dangerous to life on the ground, but for satellites and astronauts, they matter a great deal. When the magnetic field changes, weakens, shifts, or gets stirred up by solar storms, the shape and intensity of these belts can change too. You imagine a satellite passing through this invisible terrain, its instruments humming, its circuits delicately balanced. During calm magnetic conditions, everything runs smoothly. During disturbances, things get quirky. Sensors may register phantom signals. Memory bits can flip. Electronics can hiccup. Engineers call these single-event upsets, which sounds mild until you remember that satellites can't exactly be rebooted by climbing a ladder. A light joke floats by. Space is basically the worst place to need tech support. One quirky tidbit that fits nicely here: the South Atlantic anomaly shows up again, that region where the magnetic field is weaker and the inner radiation belt dips closer to Earth. Satellites passing through it are often programmed to shut down sensitive instruments temporarily, like closing your eyes while walking past a bright light. The anomaly has been slowly changing shape and drifting westward, reminding engineers that the magnetic field's quirks aren't static. Historians still argue whether early satellite failures in the 1960s were properly understood at the time, or whether magnetic and radiation effects were underestimated in the rush to get hardware into orbit. Space exploration, like most human endeavors, learned by breaking things first. As you let that settle, consider what happens if the magnetic field weakens significantly, as it does during reversals or excursions. The radiation belts could become more intense closer to Earth. Satellites in low Earth orbit might experience higher radiation exposure, shortening their lifespans or increasing the risk of malfunctions. This isn't an apocalypse scenario. It's a budgeting and engineering problem, which is somehow both less exciting and more real. Designers already plan for this. Modern satellites use radiation-hardened components, redundant systems, and error-correcting software. They expect space to be rude. If the magnetic field changes, future designs will quietly compensate. Thicker shielding here, smarter software there, humans adapting again without much ceremony. There's a fringe idea occasionally floated in popular science, that a severe weakening of the magnetic field could make spaceflight nearly impossible. In reality, it would make it more expensive and more cautious, not impossible. Astronauts already limit time spent in higher radiation zones. Missions are planned around solar cycles. Historians still argue whether public fear around radiation owes more to Cold War anxieties than to actual measured risk. You picture the International Space Station gliding overhead, a bright dot crossing the night sky in silence. It passes through Earth's magnetic environment every 90 minutes, dipping in and out of protected regions. Its crew monitors radiation levels carefully, but they sleep, eat, and work normally. The magnetic field isn't a wall, it's a gradient. A soft buffer that reduces what reaches them. Another gentle joke drifts in. Earth's magnetic field is basically space SPF. Not perfect, but you'd definitely miss it if it were gone. Solar storms add another layer to the story. When the sun erupts, blasting clouds of charged particles outward, Earth's magnetic field absorbs the hit, compressing on the sunward side and stretching into a long tail behind the planet. Satellites caught in this shakeup can experience increased drag, orbital changes, or temporary signal loss. This already happens today. It's not theoretical. It's just rare enough that most people don't notice. Historians still argue whether the famous 1859 Carrington event, a massive solar storm, would have caused significant satellite damage if modern infrastructure had existed at the time. The consensus is yes. But how much remains debated? It's a reminder that magnetic shielding and technology are part of the same system now, intertwined. As your thoughts slow, there's something comforting in how methodical all of this is. The magnetic field changes, space conditions respond, engineers adapt. No drama, no panic, just a long conversation between physics and problem solving. You don't need to track satellites tonight or worry about radiation belts shifting. They're doing their quiet work above you, protected by a field that has been changing for billions of years and still manages to hold things together most of the time. The planet hums, the satellites glide, the magnetic field bends and breathes around them all. And you, far below, can let that invisible choreography fade into the background, trusting that even in a restless sky, when there's a lot of quiet competence keeping things running while you rest. You drift a little lower now, closer to the edge of space where the atmosphere thins and human activity begins to feel the magnetic field more directly. This is the altitude where astronauts float, where long-haul flights arc across the poles, and where invisible particles carry a bit more energy than they do down on the ground. This is where radiation enters the conversation, gently but inevitably. A mainstream historical fact anchors you here. Earth's magnetic field helps deflect many high-energy charged particles from the sun and from deep space, reducing radiation exposure at the surface. The atmosphere does the heavy lifting, but the magnetic field decides where much of that energy goes before it ever reaches the air. Without it, radiation levels at high altitudes would be noticeably higher. You imagine standing on a mountaintop, thin air around you, sky feeling closer than usual. Even there, you're well protected, but climb higher, into an airplane cruising at 35,000 feet or a spacecraft orbiting Earth. And the balance shifts. Radiation exposure increases, not enough to be immediately dangerous, but enough to be measured, monitored, and managed. Airline pilots and flight crews are among the most radiation-exposed workers on the planet, though still well within safety limits. Their exposure varies with altitude, latitude, and solar activity. Flights near the poles receive slightly more radiation because Earth's magnetic field funnels particles toward those regions. That's why some polar routes are adjusted during periods of strong solar storms. As this isn't panic, it's procedure. Historians still argue whether early concerns about aviation radiation were taken seriously enough when high-altitude jet travel became common in the mid-20th century, or whether the risks were initially underestimated in the rush to make flying faster and farther. If the magnetic field weakens, as it does during excursions or reversals, radiation exposure at high altitudes would increase modestly. Airline crews might see higher annual doses. Astronauts would need more shielding or shorter missions. Space agencies already model these scenarios. They're not caught off guard by the idea. It's folded into long-term planning, a quirky tidbit to hold on to. Bananas are naturally radioactive. Airline crews jokingly measure radiation exposure in banana-equivalent doses because it's a relatable comparison. And even with a weaker magnetic field, you'd still need a lot of flights or a lot of bananas to approach harmful levels. You can feel how this topic often sparks fear online, especially late at night. Radiation is invisible. The magnetic field is invisible. Put them together and imagination fills the gap. But the reality is slower, quieter, and far less cinematic. Historians still argue whether public anxiety around radiation owes more to nuclear weapons history than to everyday environmental exposure. There's a fringe hypothesis that during the Lachance excursion, increased radiation may have contributed to changes in human behavior or biology, possibly influencing migration patterns or even artistic expression. Some point to cave art appearing around that time as evidence of humans spending more time indoors. It's an intriguing idea, mantled but heavily debated. Historians still argue whether the timing is meaningful or coincidental. As you float with that thought, notice how adaptable humans are. If radiation levels slowly increased over centuries, technology and behavior would shift just as slowly. Better shielding, adjusted flight paths, more attention to space weather, no sudden alarms, just incremental adaptation. Astronauts already live with this reality. They track radiation exposure carefully, plan spacewalks around solar conditions, and rely on Earth's magnetic field as part of their protection. Even on the International Space Station, they are still partially shielded. Beyond that, on missions to the Moon or Mars, the lack of a strong magnetic field becomes a much bigger challenge. That's a future problem being worked on now, piece by piece. And another soft joke drifts in. Earth's magnetic field is like a bouncer who doesn't stop everything, but definitely keeps the worst troublemakers out. You breathe slowly and imagine radiation not as a menace, but as a background drizzle, mostly blocked, occasionally heavier, rarely disruptive. The magnetic field tilts the umbrella, the atmosphere is the coat. Together, they keep life comfortable enough to flourish. What's especially calming is the timescale. Magnetic weakening isn't a switch, it's a slope. Any increase in radiation would be gradual, giving ecosystems and civilizations time to adjust. Past life on Earth endured periods of weaker magnetic protection and came through with remarkable resilience. You don't need to worry about this tonight. You're not at cruising altitude. You're not in orbit. You're wrapped in air, gravity, in a magnetic field that even at its weakest has never simply given up. As your thoughts slow further, radiation fades back into abstraction, a concept more than a concern. The invisible systems doing their work return to the background, where they belong. And here, close to the ground, close to rest, you can let go of the high-altitude worries. The sky can handle itself for now. You're allowed to stay grounded, breathing easily, letting the planet's layered protections do what they've done for a very long time. You drift even closer to the surface now, where the effects of the magnetic field are no longer about spaceflight or high-altitude exposure, but about the quiet infrastructure humming beneath everyday life. Wires, transformers, power stations, the things you only notice when they stop working. This is where Earth's magnetic field reaches into the grid. A mainstream historical fact anchors you gently here. Strong geomagnetic storms, driven by solar activity interacting with Earth's magnetic field, can induce electrical currents in long conductors like power lines and pipelines. These geomagnetically induced currents, or GICs, can overload transformers and damage electrical infrastructure. This isn't speculation, it has happened. The most famous example occurred in March 1989, when a geomagnetic storm triggered by a solar eruption caused a major power outage in Quebec. In less than 2 minutes, the grid collapsed, leaving millions without electricity for hours. No explosions, no fireballs. Just a sudden, quiet darkening as systems tripped and shut down to protect themselves. The sun nudged the magnetic field. When the magnetic field nudged the grid and the lights went out. Historians still argue whether that blackout was inevitable given the technology of the time, or whether better preparation could have prevented it. What's clear is that it became a wake-up call. Utilities around the world started paying closer attention to space weather. You imagine electricity flowing like a river through cables, steady and predictable. During a geomagnetic storm, that river gets extra currents added from an unexpected direction, like a sudden sideways push. Transformers designed for a certain flow can heat up, vibrate, or fail. The longer the lines, the stronger the effect, which is why high-latitude regions with long transmission lines are more vulnerable. A quirky tidbit worth keeping. Pipelines also feel these induced currents. Engineers monitor them carefully because stray electrical currents can accelerate corrosion. Even buried metal knows when the sun is misbehaving. As the magnetic field changes over long periods, weakening or becoming more irregular, Earth may become slightly more sensitive to solar storms. This doesn't mean constant blackouts. It means that strong storms could have broader effects. Power grids might need more protection, better monitoring, faster responses. Again, this is an engineering challenge, not a cinematic apocalypse. Historians still argue how often truly extreme solar storms occur. The Carrington event of 1859 is the usual benchmark, but was it a once-in-a-millennium event? Or are we simply lucky it hasn't happened again in the age of satellites and smartphones? The evidence is still being sorted out, tree rings and ice cores quietly holding clues. You can feel how this topic often triggers modern anxiety. Electricity feels fragile because it's everywhere, but the reality is more reassuring. Grid operators already monitor space weather forecasts. Satellites watch the sun constantly. When a storm is coming, systems can be adjusted, loads reduced, and vulnerable components protected. It's not perfect, but it's not blind either. A light joke drifts through, the sun throws a tantrum, and Earth responds by unplugging a few things until it calms down. There's a fringe idea that sometimes pops up in discussions of ancient history, that solar storms interacting with a weaker magnetic field might have caused unexplained technological failures in early electrical systems, like telegraph lines in the 19th century. In fact, telegraph operators during the Carrington event reported sparks, shocks, and messages being sent without batteries connected. It must have felt like magic, or mischief from the sky. Historians still argue whether those accounts were exaggerated by the novelty of the technology or accurately describe just how intense that storm really was. Either way, they remind you that the Sun-Earth connection isn't new. We've just added more wires since then. You imagine a future where the magnetic field is weaker and the sun is active. Grid designs evolve. Transformers become more resilient. Decentralized power sources reduce the impact of large-scale failures. Adaptation happens quietly, in planning documents and hardware upgrades, not emergency sirens. What's calming is how rarely these extreme interactions actually occur. Most geomagnetic storms are mild, causing little more than enhanced auroras and minor satellite adjustments. The system absorbs them like a deep breath and moves on. Another gentle joke floats by. Earth's power grid and the sun have a complicated relationship, but most days they manage to stay civil. As your thoughts slow, you realize that even here, where the magnetic field touches something as intimate as your lights and outlets, it does so indirectly. It doesn't reach up and flip switches. It nudges currents, stretches fields, and leaves humans to decide how robust they want their systems to be. And humans, for all their flaws, are very good at reinforcing things they care about. So tonight, even as electricity hums softly around you, or maybe not at all if you've turned everything off for sleep, you can trust that the planet's magnetic moods are known, studied, and planned for. The lights might flicker someday, briefly, but the world won't forget how to glow. You let that thought settle, warm and steady, as the deeper systems fade back into the background. The grid hums, the sun spins, the magnetic field bends between them, and you rest, comfortably unplugged from the need to worry about any of it right now. You drift away from wires and transformers and into something quieter, something alive. The magnetic field isn't just a concern for engineers and satellites. Long before humans built grids or compasses, other creatures were already listening to it, reading it, and using it as a guide. This is where animals enter the story. A mainstream historical fact settles in here. Many animals can sense Earth's magnetic field and use it for navigation. Birds, sea turtles, salmon, whales, bees, and even some bacteria have demonstrated magnetoreception, the ability to detect magnetic cues and orient themselves accordingly. This isn't instinct alone. It's biology tuned to a planetary signal. You imagine a migratory bird lifting off at dusk, wings cutting through cool air, heading toward a destination it has never seen. No map, no compass in its beak. And yet it knows which way to go. Experiments have shown that altering the magnetic field around birds can change their orientation, gently confusing them, like rotating the room while someone's eyes are closed. Historians still argue exactly how magnetoreception works in every species. One leading idea involves tiny crystals of magnetite in animal tissues, acting like microscopic compass needles. Another involves quantum effects in light-sensitive proteins in the eyes, where magnetic fields influence chemical reactions. Yes, quantum biology. Nature apparently enjoys showing off. A quirky tidbit worth holding on to. Certain bacteria align themselves with Earth's magnetic field and swim along it, helping them find optimal depths in water or sediment. They don't know they're navigating, they just are. Even microbes, it seems, have a sense of direction. As you imagine the magnetic field changing, weakening, wandering, becoming more complex, you might wonder what happens to these animals. The answer so far is reassuring. Past magnetic reversals did not wipe out migratory species. Fossil records and genetic evidence suggest continuity, not collapse. Animals adapt. They rely on multiple cues: the sun, stars, smells, landmarks, and learned routes. The magnetic field is one layer, not the whole map. Historians still argue whether periods of magnetic instability cause temporary increases in navigational errors among animals, or whether those effects are too subtle to leave a clear trace in the record. A few modern studies suggest that strong magnetic disturbances can disorient birds briefly, but they often recover quickly once conditions settle. You picture a sea turtle hatchling scrambling toward the ocean, guided partly by the slope of the beach, partly by the glow of the horizon, and partly by magnetic cues that tell it where it is in the vast ocean. Years later, it may return to the same region to nest, guided again by that invisible grid. It's astonishing. And yet it has worked for millions of years through countless magnetic shifts. There's a fringe hypothesis that changes in the magnetic field could subtly influence animal evolution, favoring species that rely less heavily on magnetoreception or that integrate it more flexibly. It's a plausible idea, but evidence is thin. Historians still argue whether evolutionary pressures from magnetic variability are significant compared to climate, predators, and habitat change. As your breathing slows, you notice how gentle this relationship is. Animals don't panic when the magnetic field fluctuates. They don't cling to a single signal. They adjust, recalibrate, and continue. It's a quiet lesson in resilience. And a light joke drifts through. Migratory birds don't rage quit when north moves. They just shrug and double-check the sun. Humans, too, may have once been more attuned to subtle environmental cues. Some researchers have wondered whether early humans had a rudimentary magnetic sense that faded as tools and technology took over. There's no strong evidence for this, but the idea persists, a kind of nostalgic longing for a deeper connection to the planet. Historians still argue whether this is science or sentimentality. What's clear is that modern humans rely far less on magnetoreception than other species. We outsource orientation to devices, signs, and satellites. That makes us vulnerable in different ways, but it also means changes in the magnetic field don't directly scramble our instincts. We notice effects indirectly, through systems and infrastructure, not through an inner sense suddenly spinning. As you imagine a world with a weaker or more chaotic magnetic field, you see animals continuing to migrate, perhaps with slightly more variation, slightly more reliance on other cues. Life adapts in layers. Nothing hinges on a single thread. Another gentle joke floats by. If animals can handle a flipping magnetic field, surely we can handle updating a map. You let that reassurance settle. The magnetic field is not a tyrant dictating behavior. It's a background signal, a guide among many. When it changes, life listens, adjusts, and moves on. And tonight, as you rest, you can imagine countless creatures across the planet navigating quietly under the same invisible field you are, each tuned to it in their own way. None of them losing sleep over where North decided to wander today. You drift from animals back to yourself, back into the human body, where questions about the magnetic field often become more personal and sometimes more anxious. It's one thing to imagine satellites glitching or birds recalibrating. It's another to wonder quietly what all this invisible shifting might mean for you. This is where fears tend to gather. A mainstream historical fact sets a steady foundation here. There is no credible scientific evidence that normal variations in Earth's magnetic field directly harm human health. Humans have lived through magnetic reversals, excursions, and long periods of weaker field strength without clear links to disease spikes, reduced lifespan, or biological breakdown. The fossil record, archaeological record, and modern epidemiology all point in the same calm direction. And yet, the worry persists. Part of it is because magnetism feels intimate. It interacts with electrons. Nerves use electrical signals. Hearts beat with bioelectric rhythms. It's tempting to imagine that a changing magnetic field might tug on these processes like unseen fingers. But in practice, Earth's magnetic field is extremely weak compared to the electrical forces operating inside your body. MRI machines, for example, use magnetic fields tens of thousands of times stronger than Earth's, and even those are tightly regulated for safety. You breathe slowly and let that comparison sink in. Historians still argue whether early 20th century fears around magnetism, sparked by the rise of electricity, radio waves, and new medical technologies, laid the groundwork for modern anxieties about invisible forces. When something can't be seen or felt directly, imagination often rushes in to fill the gap. A quirky tidbit to hold gently. Your body already contains tiny amounts of magnetite, the same magnetic mineral found in lodestones. It's been detected in the human brain, though its purpose there remains unclear. Some researchers once speculated it might relate to navigation or sensing magnetic fields. Today, most scientists think it's either a byproduct of normal biology or something picked up from the environment. Historians still argue whether this discovery says anything profound or is just magnetism being magnetism again. You may have encountered the term electromagnetic hypersensitivity, where people report headaches, fatigue, or other symptoms they attribute to electromagnetic fields. Carefully controlled studies, however, consistently show that symptoms don't correlate with actual exposure when participants don't know whether fields are present. The suffering is real, but the cause appears to be complex, involving stress, expectation, and the human brain's remarkable ability to create physical sensations from worry alone. That's not a judgment. It's an observation about how deeply perception shapes experience. If Earth's magnetic field were to weaken significantly, the most direct health-related change would still be indirect. Slightly increased radiation exposure at high altitudes and in space, as you've already drifted through. For people on the ground, protected by thick air and gravity, the difference would be negligible. No sudden illness. No magnetic flu season. Historians still argue whether subtle biological effects of long-term magnetic variability could exist but remain undetectable against the noise of everyday health factors like diet, stress, pollution, and genetics. It's a fair question, but so far magnetism has failed to stand out as a major player. There's a fringe idea that circulates every few years, usually dressed up in ominous headlines, that a weakening magnetic field could disrupt human brainwaves or emotional states. The evidence for this is thin to non-existent. Brain activity operates at electrical scales completely divorced from the strength of Earth's field. If magnetism influenced mood so directly, you'd expect people living at different latitudes, where the field strength varies naturally, to experience consistent psychological differences. Or they don't. A light joke drifts through here. If Earth's magnetic field controlled emotions, rush hour traffic would be a lot easier to explain. What's more interesting is how fear itself behaves. Anxiety spreads faster than data, especially when the topic involves the planet, the future, and forces beyond individual control. The idea of a changing magnetic field taps into a deeper unease about stability, about whether the systems supporting life are as solid as they feel. But history offers reassurance. Humans lived through the Lachance excursion, through full reversals, through periods when the magnetic field was far weaker than it is today. They painted caves, made tools, raised children, and worried about very immediate things like weather and food, not cosmic shielding. You imagine one of them sitting by a fire, unaware that the magnetic poles were doing something unusual overhead. Their heartbeat stayed steady. Their thoughts wandered. Their body carried on. Another gentle joke floats by. If magnetic reversals caused headaches, archaeology would be full of ancient aspirin. Modern medicine keeps a close eye on environmental factors that genuinely affect health. Air quality, pathogens, nutrition, radiation from medical procedures. These are all monitored carefully. Geomagnetism simply doesn't show up on the list of primary concerns. When scientists talk about magnetic field changes, they talk about satellites, navigation, and infrastructure first, not hospitals. Historians still argue whether public conversations would be calmer if slow planetary processes were taught more clearly in school, as instead of being rediscovered through alarming headlines every few decades. Fear loves novelty. The magnetic field, despite being ancient, is constantly framed as if it just started misbehaving yesterday. As you settle deeper, there's a soft realization waiting for you. Your body is robust. It evolved under a sky full of radiation, on a planet with a restless core, inside a magnetic field that has never been perfectly stable. You are not finely tuned to a single setting that can slip out of alignment. You are adaptable by design. You don't need to shield yourself. You don't need special equipment. You don't need to worry that north moving a little faster will somehow tug at your thoughts or your heart. The forces shaping your health are much closer, much louder, and much more manageable. When another small joke drifts in, the biggest threat to human health remains chairs, not magnetism. As your breathing evens out, the fears soften into facts, and the facts settle into the background where they belong. The magnetic field can keep doing its slow, invisible dance without intruding on your well-being. Your body will keep doing what bodies do best, maintaining balance amid constant, gentle change. And tonight, you don't need to monitor any of it. You can let your muscles relax, your thoughts loosen, and trust that whatever the planet is quietly adjusting far below and far above, it isn't asking anything of you right now. You drift outward again, not into space this time, but into the quiet spaces where planning happens. Conference rooms, control centers, lines of code written by people who never expect you to know their names. When this is where technology meets a changing magnetic field, not with panic, but with anticipation. Because one of the least dramatic truths about modern civilization is this: it already assumes the field will change. A mainstream historical fact settles in here. Earth's magnetic field has been drifting measurably since scientists first began mapping it, and modern navigation, communication, and positioning systems are explicitly designed to account for that drift. The World Magnetic Model, used by everything from smartphones to submarines, is updated regularly to keep pace with the moving north. When the field surprised scientists by drifting faster than expected in the early 21st century, the response wasn't alarm, it was an early update. Software patch. Problem handled. You imagine the magnetic field quietly shifting while somewhere else. How so server updates a table of numbers. Most users never notice. Their maps still work. Their planes still land. Their ships still arrive where they intended. This is adaptation at its calmest. Historians still argue whether this quiet resilience is one of modern society's greatest strengths or one of its most underappreciated features. Big systems don't survive by being rigid. They survive by assuming change is normal. GPS itself doesn't rely on magnetism, which surprises a lot of people. It depends on satellites, atomic clocks, and relativity. Yes, relativity, correcting for time differences caused by motion and gravity. But magnetism still matters as a backup, a cross-check, a fallback when satellite signals are weak, jammed, or unavailable. Aviation, maritime travel, and military systems all use layered navigation. Satellite, inertial, in magnetic, visual. Redundancy is the real hero here. A quirky tidbit worth enjoying. Some smartphones contain multiple magnetometers, not just for navigation, but to help detect orientation, motion, and even whether a case or accessory is attached. Your phone quietly senses magnetism all day long without making a fuss about it. As the magnetic field changes, engineers don't ask how to stop it. They ask how to work with it. Navigation charts are updated. Runways are renumbered. Algorithms are tweaked. Satellite shielding is improved. Space weather forecasting becomes a little more refined. None of this requires a dramatic shift in daily life. It happens gradually, like maintenance on a very large, very old building that never quite closes. Historians still argue whether future generations will look back on this era as one of remarkable foresight or just adequate preparation that happened to be enough. It's hard to judge resilience while you're inside it. You let your thoughts wander through a control room late at night. Screens glow softly. Data scrolls. Somewhere, someone notices a small anomaly. Nothing urgent, just a deviation from expected values. A note is made, a model is adjusted. The system absorbs the change. The magnetic field keeps drifting, and technology keeps pace, step for step. There's a fringe idea that occasionally appears in speculative writing, that a dramatic magnetic reversal would instantly cripple modern technology. In reality, it would be a slow challenge, not a sudden collapse. The field would weaken over thousands of years. None, that's not a countdown. It's a long conversation. Technology would evolve during that time, just as it always has. Another gentle joke floats by. Humans can't stop the planet from changing, but we are very good at updating the user manual. Even power grids, which feel fragile when you think about them too hard, are becoming more resilient. Distributed energy sources, smarter transformers, real-time monitoring of geomagnetic activity, all of these reduce vulnerability to magnetic storms. The future grid is less like a single spider web and more like a mesh, flexible and forgiving. Space agencies plan missions years or decades in advance, factoring in solar cycles and long-term magnetic trends. Engineers designing spacecraft for deep space assume less magnetic protection and build accordingly. When the magnetic field changing doesn't break these plans, it's already part of the equation. Historians still argue whether humanity's growing reliance on technology makes us more vulnerable to planetary changes or more capable of adapting to them. The answer, as usual, is probably both. But vulnerability doesn't mean helplessness. It just means awareness matters. You can feel how different this tone is from the way big changes are often discussed online. There, everything is urgent. Everything is breaking. Here, in the slow world of engineering and planning, change is expected, budgeted for, and quietly addressed. No countdown clocks, just spreadsheets and simulations. A small joke drifts in. The magnetic field moves, technology sighs, and someone schedules a meeting about it. But what's especially soothing is realizing how many times this has already happened. North has wandered before. The field has weakened before. Solar storms have disrupted systems before. Each time adjustments were made. Each time the world continued in a slightly updated configuration. You imagine future historians looking back at this period, noting how little fuss was made about a very big planetary process. They might marvel not at the drama, but at the boredom. The magnetic field drifted, humans adapted, life went on. Another quirky tidbit, some modern navigation systems automatically switch between magnetic and true north depending on latitude and context, without the user ever being told. Your sense of direction is already being gently managed by machines that don't mind which way the field leans today. As your breathing slows, much of the idea of adaptation becomes less abstract and more personal. You adapt every day, to light, to noise, to temperature, to routine. Technology does the same, just on a different scale. The planet changes, systems adjust. No one needs to stay perfectly still. Historians still argue whether the greatest risk comes from change itself or from refusing to acknowledge it early enough. So far, with Earth's magnetic field, acknowledgement has come with plenty of lead time. Thousands of years of it. You don't need to prepare for anything tonight. No updates required, no settings to change. The systems around you are already tuned to a moving planet, quietly compensating while you rest. And that might be the most comforting thought of all. The magnetic field doesn't demand heroics. It doesn't require vigilance from you. It just exists, shifts, hums, and lets human ingenuity handle the details in the background. You can let that responsibility go for now. The engineers are awake. The models are running. The planet is doing what it has always done. And you, wrapped in layers of adaptation you never had to consciously design, can sink a little deeper into rest, trusting that slow change and quiet competence make a very reliable pair. You drift gently backward once more, not into numbers or models this time, but into human stories stretched thin across deep time. Camps, villages, early cities, long nights lit by firelight and stars. Through all of it, the magnetic field keeps changing, flipping, weakening, strengthening, entirely unnoticed by the people living their lives beneath it. This is where civilizations pass quietly under past magnetic flips. A mainstream historical fact settles in here. The last full magnetic reversal happened around 780,000 years ago, long before writing, agriculture, or cities. Early humans lived through it without any evidence of collapse, confusion, or biological stress tied to the event. Tools improved, migration continued, culture evolved. Whatever the magnetic field was doing above them, it did not interrupt the human story in any obvious way. Later excursions, like the Lachance event roughly 42,000 years ago, occurred during a time when Homo sapiens and Neanderthals both walked the earth. Cave paintings appeared. Music may have emerged. Symbolic thought deepened. Some researchers have speculated about links between increased radiation, environmental stress, and cultural change. But historians still argue whether those timelines overlap meaningfully or simply coexist without causation. You imagine a small group of humans sheltering from cold, painting shapes on stone walls. They don't know North has gone a little strange. They don't know the magnetic field is weaker than usual. They just know the fire is warm, the cave is dry, and tomorrow requires food. The planet's invisible adjustments never enter the conversation. A quirky tidbit fits softly here. Archaeologists can sometimes determine the age of fired clay or hearths by analyzing the magnetic orientation locked into them when they cooled. Ancient fireplaces quietly recorded Earth's magnetic field direction, acting as accidental data loggers long before science existed. History literally baked magnetism into daily life. As civilizations grew, Sumer, Egypt, what China, the Indus Valley, the magnetic field continued its slow wander. Compasses would not arrive for thousands of years. Navigation relied on stars, winds, coastlines, and memory. Even if the field had been weaker or more chaotic at times, it would have mattered very little to societies not using it as a tool. Historians still argue whether any ancient myths describing a sky out of order or a confused world might reflect periods of unusual auroral activity during magnetic instability. It's tempting to read meaning into these stories, but evidence remains poetic rather than precise. What stands out is continuity. No civilization collapsed because the magnetic field shifted. No agricultural system failed because North moved. The changes were too slow, too subtle, too removed from daily survival to demand attention. Shomer light joke drifts through. Empires rose and fell, and the magnetic field didn't even get a footnote. You let that perspective settle. The fear around magnetic change often comes from imagining modern systems suddenly stripped of support. But most of human history unfolded without relying on magnetism at all. Civilization is not magnetically fragile. It's socially complex, environmentally sensitive, and occasionally self-sabotaging. But magnetism has never been the villain in its story. There's a fringe idea that sometimes surfaces, that a future reversal would be uniquely dangerous because modern society is more technologically dependent. That's partly true and partly misleading. Dependence comes with awareness. Monitoring, redundancy, and adaptation already exist precisely because we know systems can be disrupted. Past humans didn't need that awareness. They lived inside the change without naming it. Historians still argue whether modern humans underestimate their own adaptability because change now feels faster and louder. But magnetic change remains one of the slowest processes the planet offers us. And now, as this section begins to soften, everything slows further. The words stretch out, sentences lengthen, edges blur. You imagine the planet at night, turning steadily, magnetic field flowing around it like a deep, invisible tide. No alarms, no urgency. Just motion continuing, because motion is what planets do. You are safe inside this slowness. The field does not rush. It does not surprise. It gives centuries of notice before becoming anything new. You breathe in and out and let the idea of geological patience seep into you. Whatever changes come, magnetic or otherwise, arrive gradually, layered gently on top of what already exists. Nothing is yanked away. Nothing vanishes without warning. The people before you slept through magnetic shifts. The people after you will too. Tonight, the planet holds you the same way it held them, quietly, without commentary, without expectation. The invisible systems continue their work, far beyond your need to watch or worry. Your thoughts can loosen now. Your attention can drift. The story does not need you to stay awake. The magnetic field turns, the earth hums, and you rest, carried by a world that has been practicing change for billions of years. You drift onward, past the comfort of ancient continuity, into a question that tends to surface whenever the magnetic field comes up in conversation. Usually whispered, and usually late at night. Could it just stop? Could Earth's magnetic field collapse entirely, leaving the planet naked to space? The idea sounds dramatic, cinematic, and deeply unsettling. A planet suddenly stripped of its invisible armor, skies blazing, technology failing, life scrambling. It's the kind of scenario that sticks in the mind because it feels absolute. Either the shield is there or it isn't. But reality, as usual, is slower and far less interested in clean endings. A mainstream historical fact anchors you gently here. Earth's magnetic field is generated by the geodynamo in the liquid outer core, and as long as that molten metal continues to move, some form of magnetic field will exist. A complete collapse would require the outer core to stop convecting entirely, something that would only happen if Earth cooled dramatically or underwent a major internal restructuring. Neither is remotely imminent. You imagine the outer core again, that slow, glowing ocean of iron, still turning, still restless. It doesn't know about your worries. It doesn't know about headlines. It just keeps moving because heat is still flowing outward from the inner core, because the planet is still alive on geological timescales. Historians still argue whether Earth's magnetic field has ever fully shut down since it formed. Some evidence suggests it may have been weaker in the planet's early history, possibly even intermittent. But weaker is not the same as gone. Even a reduced field offers some protection, and Earth's thick atmosphere fills in many of the gaps. A quirky tidbit to hold close. Mars once had a magnetic field too. Geological evidence shows it shut down billions of years ago when the planet cooled and its core solidified. The result was an instant catastrophe. It was a very long, very slow loss of atmosphere over hundreds of millions of years. Collapse, if you can call it that, happened on a timescale so long it barely resembles the word. Earth is not Mars, it's larger, hotter inside, still very much in motion. You let that comparison settle. When people talk about magnetic collapse, they often imagine something sudden, like flipping a switch. But planetary processes don't do switches. They do gradients, slopes, long transitions that give everything time to respond. Even during magnetic reversals, the field doesn't disappear. It weakens, becomes disorganized, sprouts multiple poles, but it remains. Think of it less like a shield dropping and more like an umbrella turning inside out in the wind. Less elegant, maybe a little leaky, but still doing something. A light joke drifts through. Earth's magnetic field doesn't rage quit. It just takes messy breaks. If the field were to weaken far beyond anything seen in recent geological history, the most noticeable effects would still arrive in layers. Increased radiation in space, more auroras at lower latitudes, greater stress on satellites and power grids. None of that requires total collapse. None of it requires the geodynamo to stop. Historians still argue whether popular fears of collapse reflect a misunderstanding of how gradual planetary change really is. Human systems fail suddenly. Planets almost never do. There's a fringe idea that sometimes circulates online, that a magnetic collapse could happen rapidly due to some unknown tipping point in the core. The physics doesn't support this. The core is massive, sluggish, and governed by heat flow measured in millions of years. Sudden stops are not its style. You picture trying to stop a pot of thick soup from moving by gently blowing on it. That's roughly how effective sudden change is at Earth's core scale. Another quirky tidbit: even if the geodynamo were to weaken significantly, Earth would still have a magnetic field of sorts, induced by the interaction between the solar wind and the ionosphere. It wouldn't be strong, and it wouldn't be neat, but it wouldn't be nothing. Space rarely allows true absence. You breathe slowly and notice how this question softens when you zoom out. So collapse implies failure, but Earth's magnetic field isn't a machine built to spec. It's an emergent property of motion and heat. As long as those exist, something magnetic will too. Historians still argue whether humans are psychologically drawn to collapse narratives because they offer clarity. An ending, a moment when everything changes and uncertainty resolves into action. Slow change, by contrast, offers no such drama. It just keeps going. A gentle joke floats by. If Earth's magnetic field were a movie, it would be 4 hours long and mostly about character development. You imagine a far future, millions of years from now, when Earth has cooled more, when the core's motion has slowed, when the magnetic field is weaker than today. Life, if it still exists in some form, will have adapted to that reality the same way it adapted to every previous one. Not by noticing a single day when protection vanished, but by slowly becoming compatible with new conditions. That's how planets and life negotiate, incrementally, quietly. The idea of collapse often hides a deeper fear, the fear of being unprotected, of standing exposed beneath forces too large to bargain with. But Earth has never relied on just one layer of protection: atmosphere, gravity, chemistry, biology. The magnetic field is important, yes, but it's part of a team, not a lone hero. Another small joke drifts in. Earth doesn't put all its eggs in one magnetic basket. As your thoughts slow, the question loses its sharp edges. Could the magnetic field collapse entirely? In theory, given enough time and enough cooling, and yes, far beyond any horizon that matters to human civilization. In practice, for any future you could meaningfully imagine, the answer is no. It will weaken, it will wander, it will flip, but it will not vanish overnight or even over millennia. You don't need to brace for exposure. You don't need to imagine a sudden cosmic draft. The planet is not about to forget how to protect itself. And perhaps the most calming realization of all is this: even if the magnetic field were dramatically different from what it is now, life would still find a way to exist within those boundaries. It always has. It always adjusts. The field is not a promise of permanence. It's a story of persistence. So you can let that fear dissolve, replaced by something slower and steadier. Earth does not collapse easily. It transitions, it evolves, it takes its time. And tonight, as you rest beneath a sky that looks exactly the way it did when you first lay down, the magnetic field continues its patient work, unfinished, imperfect, and entirely uninterested in dramatic endings. You drift onward, carrying that softened fear with you, until another question gently surfaces. Less dramatic than collapse, but somehow more frustrating. When will it happen? When will the magnetic field flip again? Humans are very good at accepting slow change, right up until we want a date on the calendar. A time, a countdown, something to circle in red. But the magnetic field refuses to cooperate with that instinct. A mainstream historical fact settles in here. While scientists know magnetic reversals happen, they cannot predict exactly when the next one will occur. Reversals do not follow a strict schedule. Sometimes millions of years pass without one. Sometimes they happen closer together. The average interval is often quoted, but averages are not forecasts. They are summaries of the past, not promises about the future. You imagine Earth's magnetic field like a long, meandering sentence with no punctuation. It pauses, it speeds up, it changes tone, but it doesn't end where you expect. Right now, the field is weakening slightly, about 5 to 10% over the last couple of centuries. Magnetic north is drifting faster than it used to. These facts are real, measurable, and well documented, but they do not mean a reversal is imminent. Similar weakening has happened before without leading to a full flip. Historians still argue whether the current behavior represents the early stages of a reversal or just another temporary wobble. A quirky tidbit worth enjoying: some computer simulations of Earth's core show spontaneous reversals emerging from chaotic fluid motion without any external trigger. In other words, the field doesn't need a reason to flip. It just eventually wanders into a configuration where flipping becomes the easiest path forward. Even planets get tired of holding one position forever. You imagine scientists staring at streams of data, watching slow trends unfold across decades. There's no alarm bell, no threshold that once crossed means reversal confirmed, just probabilities, uncertainties, and patience. Geophysicists are used to this. It comes with the territory of studying systems that move slower than careers. Historians still argue whether early interpretations of reversal timing were overly confident, it's shaped by limited data sets and a desire for tidy patterns. The more data we gather, the messier the story becomes. That's not failure, it's realism. You might have heard claims that we're overdue for a reversal. That word sneaks in from human scheduling habits. Earth does not do overdue, it does whenever. The last reversal was 780,000 years ago, but before that, the interval varied widely. Some reversals happened after a few 100,000 years. Others waited millions. There is no cosmic metronome ticking in the core. A light joke drifts through. Earth doesn't care about deadlines. It didn't even acknowledge the Gregorian calendar. Even if a reversal were beginning right now, and there's no consensus that it is, the process would take thousands of years. Not decades, not lifetimes. Generations would come and go during the transition. Maps would update. Technology would adapt. Auroras would wander. Life would continue largely unaware. There's a fringe idea that certain seismic or volcanic patterns could hint at an approaching reversal. Most scientists remain skeptical. The core and the crust operate on different rules and timescales. Historians still argue whether correlations between surface activity and magnetic changes are meaningful or just coincidences stacked on top of each other. You feel the impatience of prediction soften into something gentler, acceptance of uncertainty. Not everything important comes with a timetable. Some things are better understood as moods rather than events. The magnetic field has moods, long ones. On another gentle joke floats by. Asking when the next reversal will happen is like asking when a cloud will change shape. Accurate only in hindsight. What's comforting is how little hangs on the answer. Whether the next reversal happens in 1,000 years or 100,000 years, the response looks roughly the same. Slow adjustment, layered adaptation, quiet monitoring. No single generation carries the burden of the change. It's shared across time. You imagine future humans looking back at our era, noting how much attention was paid to a drift that barely nudged daily life. They might smile at the concern, the same way we smile at old fears about comets or eclipses. Not because the fears were foolish, but because perspective grows with distance. Historians still argue whether uncertainty itself is the hardest thing for modern humans to tolerate. We like forecasts, we like alerts, we like to know when to worry. The magnetic field offers none of that. It simply continues. Another quirky tidbit, some ancient lava flows preserve records of very rapid directional changes during reversals, where the magnetic field may have shifted significantly over decades. Even then, those decades passed without fanfare, without global consequence, without anyone noticing North had briefly lost its way. You let your breathing slow as the need to know dissolves. You don't need a date. You don't need a prediction. The magnetic field is not a ticking clock above your head. It's a slow, wandering companion, changing at a pace that doesn't demand urgency from you. Tonight, North can drift as much as it likes. Tomorrow, too. The field can weaken, strengthen, hesitate, and wander, all without requiring your attention. And maybe that's the quiet gift hidden in this question. When something cannot be predicted precisely, it invites you to stop trying to control it and start trusting the process instead. Earth will flip its magnetic poles when it's ready, or it won't. Either way, it will take its time. And you, wrapped in that same unhurried rhythm, can let the future remain unscheduled, uncircled, and blissfully unannounced as you drift closer to sleep. You drift gently from unanswered timelines into a brighter presence. The sun, no longer as a distant star, but as an active neighbor whose moods ripple outward and meet Earth's magnetic field in a slow, invisible dance. If the field is Earth's shield, then the sun is the reason that shield exists at all. This is where solar storms meet weakened defenses. A mainstream historical fact settles in here. The sun regularly releases bursts of energy and charged particles, especially during periods of high solar activity known as solar maximum. When these particles reach Earth, they interact with the magnetic field, compressing it on the sunward side and stretching it into a long tail on the night side. Most of the time, this interaction is harmless and beautiful, but occasionally it becomes disruptive. You imagine the sun breathing out clouds of charged particles, the solar wind flowing steadily, punctuated now and then by stronger eruptions called coronal mass ejections. Earth's magnetic field meets these gusts like a flexible barrier, bending rather than breaking, guiding much of that energy around the planet instead of letting it pour straight in. Historians still argue whether early astronomers suspected a connection between solar activity and earthly disturbances. Sunspots were recorded for centuries before their link to geomagnetic storms was understood. It wasn't until the 19th century, with the rise of telegraphs and careful magnetic measurements, that the sun's influence became impossible to ignore. When the magnetic field is strong, it handles solar outbursts with relative ease. When it's weaker, as during excursions or reversals, the same solar storm can have a slightly larger impact. Not a different kind of impact, just a broader one. More intense auroras, greater stress on satellites, stronger induced currents in long conductors. A quirky tidbit worth savoring. Earth's magnetic tail stretches millions of kilometers into space, far beyond the moon's orbit, snapping and reconnecting during storms in a process that releases energy back toward the poles. Space scientists call this magnetic reconnection. It's elegant, powerful, and completely indifferent to whether anyone is watching. You let that image settle, the planet trailing a luminous, invisible wake behind it as it moves through the solar wind, like a comet made of fields instead of dust. If the magnetic field were weaker, that tail would be less taut, more easily disturbed. Solar storms would punch deeper before being redirected. But even then, Earth wouldn't be defenseless. The atmosphere would still absorb much of the energy. The interaction would simply shift downward a little, closer to systems humans care about. Historians still argue whether the Carrington event would have been survivable for modern infrastructure without major disruption. The answer depends on preparation, not magnetism alone. A weaker field would make such storms more challenging, but challenge is not the same as catastrophe. A light joke drifts through. The sun sends angry emails. The magnetic field filters them, and occasionally one slips into the inbox marked urgent. What's calming is how predictable the sun's rhythm actually is. Solar activity follows an approximately 11-year cycle, rising and falling like a slow tide. Scientists track sunspots, solar flares, and eruptions constantly. Space weather forecasting is now a real discipline, not guesswork. When the sun stirs, Earth is watching. There's a fringe idea that often pops up in discussions of magnetic weakening, that a big solar storm during a reversal would be uniquely devastating. In reality, reversals take thousands of years, and solar storms last days. The overlap of extreme conditions is possible, but brief. Historians still argue whether fear around this overlap exaggerates risk by compressing timescales that rarely align. You imagine a future moment when the magnetic field is weaker than today, and a strong solar storm arrives. Satellites switch into safe mode. Power grids reduce load. Flights reroute. Auroras brighten skies far from the poles. People notice, talk about it, maybe step outside to look up, and then it passes. Because solar storms, like the magnetic field itself, are transient. They surge, they fade. They don't linger long enough to define an era on their own. Another gentle joke floats by. The sun throws fireworks, Earth closes a few blinds, and everyone gets a show. What's especially soothing is how familiar this relationship is. The sun and Earth have been negotiating like this for billions of years. Long before humans watched space weather dashboards, the magnetic field was already handling far stronger solar winds than today's. Young stars are more violent than old ones. Early Earth endured harsher conditions and still kept its atmosphere, its oceans, and eventually its life. Historians still argue whether this early solar battering helped shape Earth's chemistry in ways that later supported biology. Protection and exposure, it seems, have always existed in balance. You let that balance become the focus. The magnetic field does not aim to block everything. It aims to shape interaction, to redirect, to soften, to manage energy rather than erase it. When it weakens, the balance shifts slightly, but it does not disappear. As your breathing slows, the sun recedes from menace to presence, bright, distant, powerful, yes, but familiar. Its storms are part of the background rhythm of the solar system, not an ambush waiting in the dark. And tonight, as the sun shines on the other side of the planet or slips below your horizon, the magnetic field continues its quiet work, meeting each particle with patient deflection. You don't need to watch the sun. You don't need to monitor the field. They've been practicing this interaction long before you arrived and will continue long after. The stormy neighbor and the bending shield keep talking in their own language of plasma and fields. And you, safely far below that conversation, can let the light fade, the sky darken, and your thoughts drift toward rest, knowing that even when the sun flares and the field flexes, the planet has room to breathe through it all. You drift farther out now beyond the details of storms and shields into comparison. One of the gentlest ways to understand Earth's future is to look sideways at other worlds that took different paths. Not as warnings carved in stone, but as quiet case studies written in dust and rock. This is where you imagine life without a strong magnetic field. A mainstream historical fact settles in here. Mars once had a global magnetic field generated by a molten core much like Earth's. Evidence locked into Martian rock shows that this field shut down billions of years ago as the planet cooled. Without a sustained magnetic shield, the solar wind slowly stripped away much of Mars's atmosphere, leaving it thin, cold, and dry over immense stretches of time. Notice that phrase slowly, hundreds of millions of years. No single generation of hypothetical Martians would have woken up one morning to find the sky gone. If anything lived there, it would have experienced gradual change. Thinner air, colder nights, shrinking water. So incremental that adaptation or retreat underground would have been the only sensible responses. Earth is often contrasted with Mars in dramatic terms, but the real difference is less poetic and more practical. Earth is larger, hotter inside, and still geologically active. Its core continues to churn. And its magnetic field persists. Its atmosphere is thicker and more tightly bound by gravity. Even if Earth's magnetic field weakened significantly, it would not suddenly become Mars. The gap between them is vast. Historians still argue whether Mars lost its atmosphere primarily because its magnetic field collapsed or because its lower gravity made it vulnerable regardless. The truth likely lies in a combination of factors. Planetary outcomes are rarely single-cause stories. You imagine standing on Mars today, dust swirling in a pale sky, the sun smaller but harsher somehow, unfiltered by thick air. Radiation levels are higher. Water is scarce at the surface. And yet, even there, life is not ruled out entirely. Subsurface ice exists. Briny water may still flow briefly. Microbial life, if it ever arose, could persist underground. A quirky tidbit worth savoring. Mars still has localized magnetic fields locked into its crust, like faint ghosts of its former shield. They don't protect the whole planet, but they do create tiny pockets where the solar wind is partially deflected. Even a planet that lost its global field didn't lose magnetism entirely. You let that soften the comparison. Loss does not mean absence. Change does not mean erasure. Venus offers another angle. It has no global magnetic field to speak of, yet it retains an extremely thick atmosphere. How? Gravity, chemistry, and sheer atmospheric mass do much of the work. The result is not gentle. Venus is hot enough to melt lead, but it proves that magnetism alone does not decide a planet's fate. When historians still argue whether Venus ever had a magnetic field or whether its slow rotation prevented one from forming. Either way, it reminds you that planetary protection comes from layers, not single systems. If Earth's magnetic field were far weaker, life would not simply vanish. The atmosphere would still exist. The ozone layer would still absorb harmful ultraviolet radiation. Oceans would still moderate temperature. Biology itself would respond, as it always has, finding niches, adjusting behaviors, favoring resilience over fragility. A fringe idea sometimes discussed is that a weaker magnetic field could increase mutation rates slightly due to higher radiation exposure, potentially accelerating evolution in subtle ways. This remains speculative and controversial. Historians still argue whether any such effect would be detectable amid the countless other drivers of evolutionary change. You imagine forests, oceans, cities existing under a different magnetic sky, auroras more common, satellites more cautious, but life continuing in its usual stubborn way. Birds still fly, humans still tell stories. Children still ask questions no one can fully answer. Another gentle joke drifts through. Life has survived asteroid impacts, ice ages, and oxygen poisoning. Magnetism isn't exactly its final boss. What becomes clear as you rest in this comparison is that Earth's magnetic field is a privilege, not a prerequisite. It makes things easier, safer, more stable. But life on Earth has never depended on perfection. It has depended on margins. Beyond good enough conditions maintain long enough for complexity to emerge, Earth, even with a weaker field, would still be comfortably within those margins for an unimaginably long time. You also realize something subtler. When people imagine life without a strong magnetic field, they often imagine human life staying exactly the same while the environment changes dramatically around it. But life and environment always change together. That's the part that fear forgets. Historians still argue whether modern humans underestimate their ability to adapt because our infrastructure feels rigid. But rigidity is often an illusion created by familiarity. Cities evolve, technology shifts, behavior adapts. We already live differently than our grandparents did under the same magnetic field. Another quirky tidbit: some planets and moons, like Jupiter's moon Europa, experience intense radiation environments but may still harbor life beneath thick ice shells. Protection can come from unexpected places: water, rock, depth. Nature is creative like that. You let the comparison end, not in anxiety, but in perspective. Earth is not balancing on the edge of habitability because its magnetic field wanders. It is a deeply buffered system with multiple overlapping protections, shaped by billions of years of negotiation between physics and chemistry. As your breathing slows, the image of Mars fades, not as a warning, but as a reminder that planetary paths diverge slowly, shaped by size, heat, motion, and time. Earth's path is still very much its own. Life here is not fragile glass waiting for one shield to crack. It is layered, redundant, and astonishingly persistent. And tonight, and while as you rest on this planet with its still moving core and still present field, you can feel how far away true vulnerability really is. Even in futures that look very different from today, life continues, altered, adjusted, but ongoing. You don't need to imagine a barren Earth to understand change. You can imagine continuity instead. A planet that keeps offering space for life to adapt. Long after any single configuration has passed, the comparison softens, the fear loosens, and Earth feels, once again, like home. You drift back inward now, away from other worlds and distant comparisons, toward the questions that remain open. Unfinished thoughts that keep scientists awake, not with fear, but with curiosity. Even after centuries of observation and decades of satellites, Earth's magnetic field still keeps a few secrets tucked quietly to itself. This is where science admits what it doesn't yet know. A mainstream historical fact settles in gently. Despite detailed measurements of Earth's magnetic field, scientists still cannot fully simulate the geodynamo from first principles at Earth-like conditions. The core is too deep, too hot, too pressurized, and too slow-moving to recreate perfectly, even in the most advanced computer models. What we have are approximations, useful, powerful, but incomplete. You imagine researchers staring at simulations of swirling liquid metal, watching virtual magnetic fields flip and wobble. The models behave like the real thing in broad strokes, but details differ. Timing slips, patterns emerge and vanish. Historians still argue whether current models are missing a crucial ingredient or whether chaos itself is the missing ingredient. A reminder that some systems are fundamentally unpredictable in detail. There's a quirky tidbit that fits nicely here. Earth's magnetic field has jerks, sudden changes in its rate of movement that happen over a few years. These geomagnetic jerks are real, measurable, and not fully understood. Something shifts deep in the core, briefly speeding up or slowing down parts of the field, like a hiccup in a very slow heartbeat. You let that image settle. Even Earth's deepest processes have moments of surprise. Another open debate circles around how tightly the core and mantle are coupled. Does heat flow unevenly from the mantle influence where magnetic anomalies appear at the surface? Do massive structures deep in the mantle, detected by seismic waves, help steer the flow of liquid iron above them? Historians still argue whether surface geology leaves a fingerprint on the magnetic field, or whether the core largely minds its own business. There's also the question of longevity. How long will Earth's geodynamo continue? Estimates vary widely, from hundreds of millions to billions of years, depending on how heat continues to escape from the core. New ideas suggest that chemical processes, not just heat, help drive convection, buying the magnetic field more time than once thought. The debate is ongoing and quietly optimistic. A fringe but fascinating idea that occasionally surfaces is whether tiny variations in Earth's rotation speed could influence the magnetic field. Day length does change slightly over time, although affected by tides and internal dynamics. Some studies hint at correlations between these changes in magnetic behavior, but causation remains elusive. Historians still argue whether these links are meaningful or coincidental echoes of deeper processes. You feel how different this uncertainty is from fear-based unknowns. These are questions born of patience, not panic. Scientists don't ask them because something is going wrong. They ask them because understanding is never complete. Another gentle joke drifts through. Earth's core refuses to give interviews, so scientists have to infer everything from vibes and math. What's calming is how open-ended this curiosity is. Not knowing exactly how or when the magnetic field will change does not paralyze science. It motivates it. Each satellite mission refines the picture. Each decade of data smooths some edges while revealing new ones. Knowledge grows sideways as much as forward. Historians still argue whether future breakthroughs will come from better simulations, deeper seismic imaging, or entirely new ways of thinking about planetary magnetism. It's possible that the most important insight hasn't been imagined yet. Science often advances that way, not by filling in gaps, but by realizing the map itself needs adjusting. You imagine a future researcher discovering a pattern no one noticed before, a subtle rhythm hidden in centuries of magnetic data. Not a warning, not a countdown, just a clearer understanding of how Earth breathes from the inside out. Another quirky tidbit: Earth is not the only body with a changing magnetic field. Jupiter's immense field shifts too. So does Mercury's. And even the Sun's magnetic field flips every 11 years. Magnetism, it turns out, is rarely static anywhere in the universe. Stability is the exception, not the rule. That realization brings a kind of relief. Earth isn't misbehaving. It's participating. As your thoughts slow, the unanswered questions stop feeling like loose threads and start feeling like open windows. The magnetic field doesn't need to be fully understood to be trusted. It has been doing its work for billions of years without asking for validation. You don't need certainty tonight. You don't need closure. The planet is allowed to keep some mysteries. In fact, it's healthier that way. A world with nothing left to learn would be far more unsettling than one with a few unanswered questions humming quietly at its core. The debates continue. The models improve. Where the field keeps flowing, and you, comfortably removed from the need to solve any of it, can let curiosity soften into calm. The unknown doesn't loom. It simply exists, patiently waiting for future minds to explore it. For now, it's enough to know that Earth's magnetic field is not a solved problem, but it is a well-loved one. Studied carefully, watched closely, trusted, even when it surprises. You can rest inside that trust. The planet is not hiding danger, only depth. You drift gently out of the laboratories and debates, leaving behind equations and models, and arrive at something much quieter. Choice. Not the dramatic kind, not the kind that demands action, but the subtle choice between panic and perspective. This is where preparation replaces fear. A mainstream historical fact settles in here. Modern governments and scientific agencies actively monitor Earth's magnetic field and space weather, sharing data globally to anticipate disruptions rather than react blindly to them. Organizations track solar activity, geomagnetic storms, and field changes continuously, issuing forecasts much like weather reports. This is not emergency science. It's routine. You imagine dashboards glowing softly in the middle of the night, numbers updating, plots shifting slightly. Most days, nothing happens. Some days, alerts are issued. Systems adjust. Life continues. Preparedness in this context is not about bunkers or survival kits. It's about awareness woven quietly into infrastructure. Historians still argue whether preparedness works best when it's visible and reassuring or invisible and automatic. With magnetic change, invisibility seems to win. The less you notice it, the better it's probably being handled. There's a quirky tidbit worth resting with. Many satellites already operate under conservative assumptions, designed to tolerate worse radiation conditions than they usually experience. Engineers build in margin because space is unpredictable. That margin is a form of calm, extra room to breathe when conditions shift. When discussions turn toward what should we do about magnetic change, the most honest answer is often, keep doing what we're doing, just a little better each year. Improve grid resilience, update navigation models, advance space weather forecasting, educate without alarming. None of these require urgency, they require patience. A fringe idea sometimes surfaces in popular media that individuals should personally prepare for magnetic upheaval, stockpile supplies, shield electronics, relocate. In reality, individual action has almost no role here. Magnetic change operates at scales far larger than personal response. Collective systems matter, coordination matters, and those systems are already in motion. Historians still argue whether modern culture has become addicted to doomsday framing because it gives people something concrete to brace against. Slow change offers no such clarity. It asks for trust instead. You feel that trust settle now. Not blind trust, but informed trust. Trust built on history, evidence, and repeated experience. The magnetic field has changed before. Humanity adapted, sometimes without even noticing. Today we notice more, measure more, now and plan more. That's an advantage, not a vulnerability. Another gentle joke drifts through. When it comes to magnetic change, the correct emergency response is carry on. What's especially calming is how preparation blends into normal progress. Strengthening power grids also makes them more resilient to storms and accidents. Improving satellite shielding benefits all missions, not just rare magnetic events. Better navigation models help pilots and ships every single day. Preparation for magnetic change is preparation for a wide range of futures, most of which are ordinary. You imagine explaining this to someone anxious about the field weakening. You wouldn't rush. You'd speak slowly. You'd say that Earth is not sneaking up on us. That change is measured in generations. Us that every important system already assumes the planet will not stay perfectly still. Historians still argue whether reassurance should come from data or from narrative. Tonight, it can come from both. The narrative is simple. Earth changes slowly. Humans adapt incrementally. Panic has never improved that process. Another quirky tidbit, even ancient societies prepared for environmental uncertainty without understanding its causes. Floodplains were mapped, seasonal cycles were tracked, redundancy was built into food storage. Preparation doesn't require full knowledge, just respect for variability. You feel your thoughts loosening their grip on the future. There is nothing you personally need to anticipate. No special vigilance required. The systems designed to watch the sky and the core are already watching. The people trained to respond are already trained. Preparedness, in this story, is not something you carry on your shoulders. It's something distributed across institutions, disciplines, and time, shared quietly, like the magnetic field itself. Another soft joke floats by. Earth adjusts, humans adjust, and everyone pretends that was the plan all along. As this section begins to fade, what remains is a sense of steadiness. Not because nothing will change, but because change has been accounted for, built into expectations, folded into design. You don't need to rehearse worst-case scenarios. You don't need to imagine dramatic interventions. You can trust the slow machinery of adaptation, the same machinery that has carried humanity through ice ages, climate shifts, and technological revolutions. The magnetic field will continue to wander, and humans will continue to notice, measure, and adjust. Life will continue in the spaces between. And you, for tonight at least, can step out of the loop of what if and rest in handled. Handled doesn't mean perfect. It means ongoing. It means watched. And that is more than enough to let your shoulders relax, your breathing slow, and your thoughts drift toward their final, quiet landing. You drift into the final stretch now, not toward answers or warnings, but toward a gentler perspective, one that pulls everything together without tying it too tightly. After wandering through cores and skies, animals and machines, fear and preparation, you arrive somewhere quieter. Acceptance. Not resignation, not indifference. Just a soft understanding of how slow, natural change fits into a world that often feels rushed. A mainstream historical fact settles here like a steady breath. Earth's magnetic field has been changing for as long as it has existed, and life has never experienced it as a crisis. From single-celled organisms to modern humans, life has unfolded under a field that wandered, weakened, strengthened, and flipped, all without demanding attention or ceremony. You imagine the magnetic field tonight as it really is. Not a headline, not a threat, but a flowing pattern wrapped around the planet, shaped by motion far below your feet and energy far above your head. It is neither perfect nor broken, it simply is. Historians still argue whether humanity's tendency to fear planetary change comes from a misunderstanding of scale. We are used to things that fail quickly: machines, plans, promises. Earth does not fail that way. So Earth changes the way mountains erode and stars age, slowly, quietly, and without drama. There's a quirky tidbit worth letting linger. If you could see the magnetic field with your eyes, it would look alive. Lines shifting gently, pulsing in response to the sun, never holding exactly the same shape twice. We often fear movement because we associate it with instability. But in planetary terms, movement is stability. You let that sink in. The field doesn't promise to stay the same. It promises to keep going. A light joke drifts through one last time. Earth's magnetic field is the ultimate background character, crucial to the plot, never asking for attention. What remains now is reassurance without denial. Yes, the magnetic field will continue to change. Yes, north will wander. Yes, auroras may brighten, satellites may adapt, Nuclear and engineers may schedule more meetings. But none of this asks you to worry tonight. Historians still argue whether the greatest challenge for modern humans is not environmental change itself, but learning how to live comfortably with slow uncertainty. The magnetic field is a perfect teacher in that sense. It cannot be hurried, it cannot be frozen. It can only be observed, respected, and allowed to unfold. You imagine Earth turning in the dark, magnetic field, flowing around it like a deep, invisible tide. Cities glow, oceans move, forests breathe. Somewhere deep inside, molten iron continues its endless, patient circulation. Everything is in motion. Everything is holding. And now, finally, you don't need to hold anything at all. Your thoughts can drift without direction. Your body can sink into stillness. The future can remain unwritten. The magnetic field will keep changing whether you're awake or asleep. It doesn't need your supervision. It doesn't need your concern. It has done this before, and it will do it again, gently, over spans of time that dwarf worry. Tonight, the shield is still there. Tomorrow, it will still be there. Long after, it will still be something. Different, perhaps, but present. You are safe inside that continuity. As the story fades, there is nothing left to solve, nothing left to anticipate. Just the steady comfort of a planet that knows how to change without falling apart, and a listener who is allowed to rest inside that knowledge. Your breathing slows, your thoughts soften. The invisible systems keep working quietly in the background. And with that, the journey eases to a close, leaving you exactly where you need to be, unbothered, unburdened, and ready to drift fully into sleep.